All right, we're going to look through our 2022 infrared software. So this is all of the software that we write to make the robot basically be able to move and do all of its functions. So auton, auto aiming, all of the climb functions, mapping the driver and operator controls to the different things that the robot can do. All of that happens in this software. So this is the very first introduction to some people. I'll try to explain things as we go, but some of it may not make sense if you're brand new to the FRC programming. All of this is in a software called VS Code. So this is what gets installed when there's a special installer that installs it specifically for FRC, and it kind of sets everything up for you. You have this button over here on the right, this W, that gives you a bunch of different WPI lib stuff that lets you build the robot code, download it to the actual robot. There's some simulator stuff, so you can run the code on the computer without having to have a robot near you, so you can do some testing in the simulator. There's a lot of things you can do here that are specific to WPI lib, so all of it's set up specifically, and it all installs pretty easily, and we'll go through how to do that a little bit later in a different session. And then what we end up doing is we use that main library, so there's a lot of stuff that other community members basically write to make it easier for us to program. So we don't have to write all of the incredibly basic information to how to talk to a motor. That's kind of already done for us. We have software that lets us do that, and so we just have to know how to use those tools to be able to get a motor to spin the way we want, to be able to configure a lot of the settings, to use the buttons in the way we want on the joysticks. All of the really low-level stuff largely is done for us. And a lot of what we're doing is integrating everything and making it work with our robot. And that still takes a lot of time and effort and testing, and reading different manuals and all the different documentation for how all the software works. A lot of time goes in there to get it to be functional. Our setup is a little bit different than sort of the default recommended setup. If you just make a template for WPI Lab in the way that they set it up, we do it a little bit differently, just because we've been developing it for quite a few years, and we think it makes a little bit more sense, and for just to meet our needs and some features we want that aren't included in the regular one. But it's not too different. So if you learned how to do ours, you can go and help somebody else relatively easily on their robot. We end up helping people at events and stuff relatively simply. Most of the methods and things all the same, just some stuff are located in different files and things. So kind of the brief overview, this is the file tree where all the different files that we use, where the actual code sits, right? So the documents kind of look like this. This is the main robot.java. And so this is what the thing that actually gets run at the beginning of the robot and tells where everything else is here. There's two different folders that we have. Library. This is all stuff that in theory doesn't need to change from year to year. A lot of this is specific stuff to mapping the Xbox controllers. There's some stuff to how the specific motors work, and they're just things that we use to make our lives a little bit easier. Some of the swerve code ends up in there where it doesn't really need to change from year to year, and or from robot to robot, and it can all kind of stay the same. Everything that's in the robot folder is mostly stuff that's specific to that robot, where there's different settings that have to change or anything like that for the specific robot. The classes that we make or the files that we make for the climber or the intake for that specific robot are all in here, and these wouldn't get reused in their entirety. A lot of times we'll use parts of them or bits of them, or we'll use versions of them in a future year, but they're not going to be identical. We actually ended up having a pretty big advantage, and a lot of teams did, going from 2021 and 2020 code to 2022, since they were both ball launching games. The software was pretty similar, so we didn't have to do a ton of move. We were able to copy a lot of the stuff from the 2021 robot that was also a swerve drive that had a rolling intake that brought in balls and launched them out with a wheeled launcher. Since the robots were the same, a lot of the methods and a lot of the things that were used to command them were also all the same. So sometimes you can be that way, but if we end up having a game where we need an elevator move up and down, or something's built entirely differently, you end up having to write those and create those things again, because they're not going to be the same. Okay, so a couple kind of basic things to know about the way the software works and just the way the robot works in general. There's a couple different modes for the robot. And so the robot starts by running its initialization. So robot init is the things that run right at the beginning. So as soon as the robot starts up, this runs one time, and it basically tells it to start up some of its data logging things. It checks if it's running on the practice bot or not. So in this case now the practice bot is 8515. So it checks which robot the code is running on, so that we can download the same code to both robots, but there's things that can be configured differently on each robot. It sets up all of the subsystems, so it basically says we have all of these are all the motors we have. This is the names of them, so we know, or the IDs for them, so we know how to communicate to the motors. Pneumatics, anything like that, sensors, all of that gets set up as it goes through and creates the subsystems. It sets up a lot of the telemetry stuff, where we have a little dashboard where we can get values back from the driver. It turns the limelight LEDs on at this stage, just in case if it's during a match we want to make sure they're on, and that's the default. There's other times where we can turn them off if we need to. There's some stuff with configuring the game pads. Just a lot of just like cleanup stuff, make sure everything's ready to run at the very beginning, and it does that once. And then throughout everything else from then on, roughly every 20 milliseconds, it's running this thing called command scheduler, and that's how we actually run all of our software. Everything that the vast majority of things that we run on the robot are all run as commands. And so there's a command that tells the robot to take the joystick values and make them into values for the motors to move the robot around. So if the driver moves the joysticks and we want to move the robot, there's a command that does that, and it's always being run by the scheduler. And that kind of just makes sure things aren't interfering with each other or anything like that. So when you hit a button, most of the time that button is starting a command, and then that command's going to end either when you release the button or maybe when something finishes or some amount of time later. But everything is done to where you push a button or you move a joystick or something, and that's being run by a command. So if the commands aren't running for some reason, nothing will work. So if we just removed this line of code right here, literally the robot would not do anything, because none of the commands would ever be run because we don't have the scheduler running anymore. And then the 3 states for the robot are disabled. So we have a disabled initialization. So anytime the robot goes into the disable state, if we just take it out of either the other 2 working states, in disabled, none of the motors can move. That's basically, it's powered on, but it's in a safe state, so nothing can move. And so it goes through and just kind of resets everything when it's in disabled. There's also autonomous, which is when the driver controllers aren't fed to the robot, so you can't use the gamepad inputs, but the robot can still do all of the actions on its own, so it's able to drive around. That's how it's the start of the match when it's doing autonomous. That all happens, but it can't read the gamepad inputs. And then teleop is the 3rd state, and that's when the driver is actually in control of the robot. We can drive it around, do everything we need. There's a couple other states that we don't use as often. Test exists. We don't currently have a good use for it. There's a test mode, so you could have different button mappings or something if you wanted to have a mode that's specific for the pit, or some other way that you're going to system check. Like we could do certain different things in a test mode. And then there's stuff that happens also just specifically when we're in simulation, this is running in addition to everything else when we're actually just simulating and it's not actually running on the real robot. Okay, so then the way the structure of the actual robot works, so once we have those modes, once we're trying to actually do things, we set up subsystems and commands. Subsystems basically translate to the mechanisms of the robot. So just like we talked about the structure of different robots last week, and when we talked about infrared specifically, there are roughly 5 subsystems. There ends up being 6 in software, a couple others that we add as subsystems but aren't really subsystems. where we have swerve, which is the drivetrain. So that's the first subsystem. Intake is a subsystem. For programming specifically, it makes a lot more sense for the ball path to be split into two subsystems. So it has indexer and feeder, and they're split. Even though we designed them in CAD and everything, they're kind of grouped as one mechanical subsystem. In software, they end up being split to two, just because it's easier to control the motors independently in their own subsystems. And then the launcher subsystem and the climber subsystem. The couple others exist that are just there kind of just to make the structure easier. Pneumatics is kind of running the compressor, making sure we have air when we need it, that sort of thing. And then the Limelight subsystem doesn't really necessarily need to be put here. This was kind of a quirk we did a while ago and we've just left it. It probably could be moved somewhere else and not be in subsystems, but it works well enough here. So we've left Limelight and some of the vision stuff in here because the commands end up acting on them, so it works in here and structurally in code, but they're not really their own subsystem. They're not doing anything. They're not moving any motors or anything specifically. So what the subsystems end up looking like, we can look at a kind of simple one. Intake is relatively simple. All it really does is it defines that the intake has like a motor. So it has a Talon FX, which is the motor controller that's on the back of the Falcon. Like it says it right on the back. So this just means it has a Falcon motor. We configure it. We tell it current limits, how fast we want it to be able to go. There's a bunch of different settings you can do for the Talons, which we'll go through at some point. The intake also has a pneumatic solenoid so that we're able to push the intake up and down. So that gets created here. And then you also tell it what its like default command is. So if nothing else is happening, what do we want the intake to do? In this case, it's pretty easy. We just want the intake to stop. We don't want the intake to be running unless the driver is pushing a button or an auton. We're telling it to intake. We don't want it to be moving at all. So its default command is just stop. And then there's a couple methods you can build for it to tell it to do different things. And so this is pretty basic, where we can literally just say intake on, and it just runs the manual output to whatever intake speed that we've set it to be. In this case, we have our intake speed set to 0.9. Like we can look at what it is. If you go over here, there's like a constant file that sets it, but normally everything will save. So I just hover over it, it tells me it's 0.9. So it's going at basically like 90% of whatever the battery voltage is at any time. We could change that. We could make it slower. We could make it a little bit faster. We could change it to 100% of the battery. We could do other ways to control it. So instead of just giving it like how much battery to control it, you could try to have it actually spin at a certain RPM if you wanted. There's all sorts of ways you could control it. A lot of times we'll try to do the simplest way that works. For something like the intake, it was fine for us just to have it spinning, and if it was slightly slower at different times, like if the battery was slightly drained and the intake spun slightly slower, it really didn't affect us that much. So we left it in the simple way. And then it also has a down and up method so that we can move the intake up and down. So it's really not that complicated for some of the basic subsystems. Other things get very complicated, so we're not going to even go through everything that's in Swerve or in some of the other ones. They get a lot more complicated, but we've tried to make the ones that can be simple as we can, so we don't have a bunch of other stuff in here that just makes it more to look through, potentially more places for errors, anything like that. So indexer and feeder. Oh, indexer got weird because we added color stuff. Without all the color stuff, indexer is also not that complicated, but because we started playing with the color stuff, they're added a bunch of methods that don't actually do anything right now because we're not color sorting. Feeder, on the other hand, is a little bit easier. There's a couple more things in there. It has some sensors to tell us where the balls are. It has to check. It runs specifically, like while it's intaking, it does some things to sort the balls and make sure they stay, and they don't actually go into the launcher. They don't go too far in the launcher, that'd be bad. And then feeder is also set up to run at a specific velocity. So as we were going through the season, we realized it used to be running the same way as intake, to where we just had it set as like feeder on, and we would just set it to some voltage. It was really low. It used to be like 0.2 or something. And then we realized that was part of our issue, is we would start missing the second shot a lot. So we would shoot 2 balls, and the first ball would go in and the second one would go over. And so what we eventually did was we figured out that we could control the velocity specifically. So instead of just having it run at some voltage, we were telling it to run at a very specific RPM. And then we were able to tune that in and make it so both balls shot at the same velocity. They were fed in at the same rate, and that solved the problem. So a lot of times, increasing the complexity, we kind of only do that when we're trying to solve a problem that is making the robot not perform well in the field. So it's missing balls, or it's not being controlled well, or anything like that. We'll try to add complexity. Most of the time we're going to try to write really simple stuff, make it work, and if it can't, then we'll make it more complex. Let's see, what time is it? Okay. The last one we can look at, because it's a little bit different. So most of these are all just motors spinning wheels. The intake, the launcher, the indexer, and the feeder are all just spinning wheels. And so they can like turn forever. The climber's a little bit different because it's on the spool. So if you turned it forever, it eventually would try to break itself. So it would just try to like keep pulling down really hard. So since it's a position system, so we're actually trying to have it like go to a certain position each time and then come back down when we're climbing. It's built a little bit differently. We tell it which motors we have again. Why does Climber only have... Oh, because it already, yeah. So it has 4 motors. It has a motor leader, follower 2 and 3. So there's 4 motors on our climb right now. And so they all get set up as Falcons. We configure them all the same. And then we have to tell it basically like how far it can actually move up and down. And so it has a specific method, set MM. MM stands for motion magic. It's like a special feature of the Falcon motors that lets us pretty conveniently move it to a specific spot that we want. And so that's what we use to tell it to go to a specific height and to come back down during like the automated button. So like the D-pad controls for the climber uses this method. And then we still almost always have some sort of fallback where we have manual control, where the driver, or in this case the operator, can move the joysticks and manually move the motors. And at that point, we still, like, they could, in theory, they could probably break some things or bend some stuff, but we try to avoid that. But so all of the other parts of the climb, so being able to like tilt, the pneumatics on the climb, those have their own methods. Pretty much any time the robot needs to do something, you have a method in a subsystem that allows that to happen. So if it needs to move a motor, if it needs to move a pneumatic, if it needs to go to a certain position or set a certain velocity, you basically have to write the methods into the subsystems, and you're telling it how it can do anything that the robot's going to do during the match, during Auton, any of it. So all of it gets written in the subsystem, and then when we'll look at commands next, we're able to go through and use those commands, or use the methods that are here, to build up commands that we can then use to map to buttons, to use during the autonomous routines, anything like that. So commands are the next things. Constants are literally just big files where we have all of like specific values where we can tune things, change things from fast to slow, anything like that. So intake constants, some of them aren't needed because some of them are a little bit more complicated, but like launcher constants make a little bit more sense. We're like, oh, this is how far, when we used to have the movable hood, we had different like angles that we could set. Some of this needs to get cleaned up because we haven't had a movable hood in a while, so we could delete those. But like here, we have the different shots for the low goal, or from when we're at the tarmac, or the far shot. So we're literally just changing these numbers to figure out, oh, the launcher's acting a little bit different, and we could go in and change that number and make it shoot a little bit further, or shoot a little bit less. Same with the vision setup. And some of these are calculated either experimentally, where we literally take the robot and just like test things. Some Sometimes we'd try to do a little bit of math to figure out some of these, like what makes sense for the formula to be able to make. So I know Emilio and Rebecca did quite a bit of this last year. So basically this was the base speed, it was spinning at this, whatever it was at the closest, and then it would just add 58 RPM per foot away that it knew it was from the goal, and that allowed us to make a lot of shots. So all of these are just ways we can go in and tune and change the code to tweak it as the hardware changes, or if we just need to adjust things, if something's not quite working on the field. A lot of times we're just going to come in and adjust constants in these various files. Okay. What the actual commands look like. We've made them a little bit simpler. This climber makes sense to look at. It's an easy one. So this is what we kind of used to have to do for any command. So for every single command on the robot, if we wanted a button to do something, we used to have to basically write its own file. So like rumble controller.java is a command that all it does is rumble one of the controllers when something happens. So if we wanted to have it rumble when it intaked a ball or something, we could do that. And we used to literally have to like copy and paste this file in and change things in here to make it do what we wanted. So in this case, all it did was it would take in which controller we're using, so like whichever gamepad we wanted to rumble, how hard we wanted to rumble. You could tell it like 0 to 1 how strong you wanted the rumble to be. And then it would just, as soon as the command would start, it would controller.set rumble, it would do it, and then when the command would end, it would set rumble to 0. But you still had to have all of these things written out here for every command. And so that got really long because we had a lot of files for every command, right? For ball intake, for launching at different speeds, depending on how we were doing it. There was a lot of files. This was only even like 3 years ago. And then what we started doing is making inline commands, so they're a lot easier. So now something like this, our ball path commands file, just lists every command that the ball path can do. So that's intake, ball path, and launcher are all done in here. It makes sense when they all get combined, because a lot of times a single button might use all 3 of those things to actually fire the ball or something. So because of that, we wanted them all in the same file. It made it easy to reference each other. And so some of them get built on each other. So if you come down towards the bottom, we have things like run indexer, which generates a command. And so this takes a speed, so we tell it how fast we want the motor to spin, 0 or -1 to 1, negatives being reverse, positives being forward. And then all it does is actually call the method that we have in the indexer subsystem, indexer.set manual output. And so it just runs that to a certain speed, and then whenever we're done running the command, it runs indexer.stop. So that's simple enough that we can then run this command. We can like map this to a button. We can use this in Auton, and we can do that for everything else too. So if we need to set a certain thing to an RPM, if we need to run the launcher at a certain speed or run the launcher at an RPM, all of these are set up so they basically act as little building blocks that allow us to make more complicated things. So like run intake exists in the same way. Intake up and intake up instant. We don't need to go into why those are different, but they help us basically do slightly different building blocks, so then we can make entire programs that actually do a lot of things. So we might want to put the intake down and intake and run the indexer and use the feeder to store the balls, and all of that can be done in a single command. So if we come up to like intake balls, so when we run the intake button, whenever the driver decides we're intaking, it doesn't just turn the intake on, it runs the intake at whatever intake speed we have, And at the same time, so along with, it puts the intake down, so it runs the pneumatics to actually deploy the intake out so it can intake a ball. At the same time, it runs the indexer, so it brings the indexer in so that the ball actually goes into the robot. So if you just did these two and you didn't run the indexer, the balls would just shoot out over the intake and would never actually go into the robot at all. So it runs the indexer at whatever our speed is that we want to run. At this point, we're using feed speed. I think we used to have a different intake and feed speed, then it wasn't working, but that's something we can play with. Feeder intake is what the feeder does to store the balls. So that has its own method somewhere, so we can you can navigate around pretty easily. So feeder intake, if you don't know what that does, you can right click and do go to definition, and it's right above it. So that's the feeder running intake balls. Somewhere. Oh yeah, feeder's running the intake balls method, which we looked at before, and that's the one that's using the sensors to say when to run and when to stop and everything else. So that's how it actually does the storage. Similar things happen for when it's actually doing the launcher RPM or anything like that. All of this basically just lets us have little building blocks that we can use to make bigger and bigger commands so that the robot can do whatever action we're telling it. As we get farther up, we can get to our actual auton commands or autonomous commands, so what it actually runs at the beginning of the match. There are a couple different versions of these. For our first 3 events of the season, all the way through state championship, we basically ran an incredibly simple auton command. So this double ball simple file right here ran a very simple command. So all it did was create a list of commands that were going to run together at the same time. So it's a parallel command group, so all these commands are going to run together unless we tell them otherwise. And so you'll see that happens in a second. So at the very beginning, we just tell it to turn the launcher on at whatever the velocity the limelight's telling it to. So limelight with limelight shot is basically saying, look at the limelight, figure out how far away we are from the goal, and turn the launcher wheel up to that velocity. And then it waits for like a quarter of a second. This is in here because we had some issues with the swerve right at the beginning. If you try moving before the swerves can like align themselves, it messes up. So we give it like a quarter of a second to spin the wheels to the right spot. And then we tell it to drive. So it literally just drives backwards for 1 second at 0.2, so 20% speed. It just drives backwards for 1 second. So we just line it up where the ball is directly, or I guess forwards. The intake is normally forwards. So it's driving towards the ball for 1 second at 20% speed. And we make sure the intake it's actually running the intake at the same time. And then as soon as it finishes that, so once that second's over, it waits another second and continues the intake, so it makes sure that the ball gets fully into the robot and gets stored ready to fire. And then it runs the feed command for 1.75 seconds. Again, these things like this could be tuned. This could be better at 2. This could be better at 1.5. It probably doesn't matter as long as the ball actually exits. It doesn't really matter. And so that actually feeds the ball into the launcher and it shoots it into the goal. And then it's done. It prints the command that says double ball done so that we know it's done if we were like seeing it on the console. And that's the entirety of that autonomous. And that was fine for like 3 events this year. We won 2 of those events and won our division at the other one. It by no means was the best auton in the world, but it was sufficient for what we needed it to do on that side of the field for a lot of our matches, and it worked well. Like, would it have been better to have something more advanced? Possibly. but because we were doing a lot of other tweaking on the robot and doing a lot of other stuff, autonomous just wasn't the priority at that point. Making sure the climb worked better, getting all of the intake, launcher, everything else to work better, getting our teleop cycles faster. Like, there was a lot of stuff that we were doing throughout those 6 weeks that was a little bit more important than Auton at the time. And then we started working on Auton going into World Champs to try to get a more complicated Auton. And that's where we started doing what's called path following. And so we can see what one of those Autons look like. And this is the one we're going to try to have working better for the Remix and for NTX. And we started doing that last Saturday of trying to tune it and make it a little bit better. And so that's 5-ball auto. So this program right here, again, a lot of these are just these building blocks that we basically just put in order and tell it how we want them to work. In this case, we're basically just telling it to follow these different paths, and I'm going to show how the paths get created here in just a second. So it's literally just telling it, like, in order what we want the robot to do. So in this case, we're telling it to turn on the limelight shot for the whole autonomous mode, so like all 15 seconds. Follow the path and intake at the same time, so it's going to go intake the first ball. It's going to intake just alone for a little bit, so it basically like pauses and intakes. It follows the path and intakes to go get the second ball. Intakes alone for a little bit. We realized it needed to have that like 1/10 of a second of intaking, or it was messing up some points. It shoots those balls, and then it follows the path back to the actual terminal to try to get the balls that the human player has or near that area. It intakes those, and then it's supposed to aim towards the goal. And we had it either aim towards the goal and then drive back, or we had it do some other, we had to do it some other things depending on what we were trying to get those last shots to do. Because that's where we ended up having problems, is we could do the first 3 balls pretty well, but it was having a hard time actually doing this step here and actually driving to the terminal. And so that's what we were trying to work on. So briefly, I can show you what it looks like to have those paths. So in our, this is what the actual folder looks like that has all the code in it. One of them is called Path Planner, and this is the tool we use to kind of generate the paths, which is just like a list of points where the robot's going to try to drive to. And Path Planner lets us do that pretty well. So we have something like this where it starts, we tell it its starting point, its ending point. So this path is really simple. It just has this one start point and end point, and it just drives backwards. And you do that for each one. So like second ball, it starts here and goes over there. Intake second ball, so it starts there, goes there. And so that's when it's launching already. And then go to terminal. It's going to be here, ideally at this like third ball. It's supposed to drive back, intake this, wait a little bit to be able to intake the one from human player. And then we can tell it to do a lot of different things. So at some point we had it driving forward to go to its second shot. So it was like driving further forward. We had it like stopping up here. That wasn't working very well. We were like missing and doing different things. So we're trying to make sure that once it actually stops here, it can get back and get to that ball correctly. This software is set up pretty nicely where it automatically deploys the path files to the robot when we need it to. So we literally can just tell it to load path based on the names. So these names here are all the exact same as the names here for the 5 balls that were for the 5-ball Auton that we're running. If we wanted to make a new path, we could, and we can make a demo or something so you can type some new name for it. We'd have to tell it where the robot was starting. So it would have some starting configuration, and you can move the robot around. We can tell it how it's going to start the match. We can tell it the next sort of point we want it to be at. You can drag around which way The robot's going to go through and do this motion. Most of the time for us lately, we haven't been doing multiple spots on the Auton paths. We were having issues with them getting accurate. So like if we told it to do this, a lot of times it wouldn't. It would just kind of drive through and not quite hit this middle point. So it was easier for us just to have it be 2 points per path, and that was working better. So if we wanted to, for some reason, to like start here and then drive back here really quickly, we could do that. You can tell it kind of where the headings are and what angles or lines you want it to take out of there. And it would ideally try to start here, and it would drive there. It would rotate while doing it. This little dot for us represents basically where the intake is. So it would start here, it would start spinning as it went, and eventually end with the intake here, pointed that way. And so we can build out whatever path we want on the field, and that's roughly what it's supposed to do. The trouble is there's a lot of steps between this and getting it to actually do it in reality. There's a lot of little tuning. So a lot of what we were doing on this past weekend was going through and trying to make sure that we could actually drive much simpler paths. So we were actually just telling it to drive, which one? So test 1 meter. So at some point we were having, this is the different version of it, but at one point we were having it just drive a single meter forward and measuring it to see if it could actually do that. Like, could it actually just drive 1 meter straight forward? Could it drive 3 meters straight forward? Could it drive 6 meters straight forward and actually stay accurate that whole time? And then if it wasn't, we could go through and try to change some of the settings to make them better. So we had to so we would actually change settings on like how big the robot thought the wheels were. That was one of the main things we were changing early. So in our constants file, we have a swerve constants. And so we have a setting that says how big the wheels are. This isn't the updated one, I didn't update this. So we went through and changed this from this number to a number that's much more accurate now. So now the robot's much more likely to know how far it actually drove. So we tell it to drive a meter, it's pretty good at actually driving that meter. We got it down to within about 1/4 inch of where it thought it was going, all the way out to 6 meters. So roughly driving 18 something feet, it was doing that within 1/2 inch or within 1/4 inch. But we still were having issues with it getting all the way to the terminal and doing that full path, so we're still having to work some things out. We'll probably do a little bit more of that tomorrow and Saturday to try to make it a little bit better at getting all the way through the autonomous. What was I going to say? So, yeah, so where the software gets built is we're basically building a lot of this stuff over and over again on like smaller bits that we can do easily. So things like just being able to tell the intake to turn on, and then they get combined into the commands, then they get combined again into the Auton commands that let us build out the entire Auton programs that we're trying to make the robot do. Those same commands also get used for teleop and for the drivers. So we didn't look at that yet. So the gamepads file is where we basically lay out how the drivers can control the robots. So we have something here where we bind the different buttons on the driver controller to a command. So we're basically saying when this button is pressed, this is the command that runs it. So some of the simple ones are like the driver's A button runs the intake balls command. The driver B button swaps us to a different control mode, so we're in like first person view mode with the robot, so we can drive through the camera correctly instead of the field control mode that we use normally in a match. The Y button is eject, so we launch the balls out through the intake side, and the X button is how we feed to the launcher. And so we go through the entire joystick mapping. I'm not going to go through it all, but it's all relatively easy to basically just be like, oh, driver is the driver controller, dot whichever button you want, dot when pressed if you want it to just happen like once when it's pressed, or while held if you want it to happen the entire time it's held. So for something like something to stop, you don't need it to happen the whole time it's held. You can just tell it to do it once. Then we have other things like the while held for the right bumper is our actual aim, so that's how the limelight aims to the goal. And then we wrote some stuff that allow us to combine buttons. And so this is why we have things like the and not button. So this means if the right bumper is pressed and the left bumper isn't pressed, do this thing. And so we can do a lot of different combinations, and this allows the drivers to have a little bit more control all in a single joystick or a single gamepad. There are a lot of specific things they can do. So the buttons up here are these and buttons, and so that's how we do the reorienting the robot to tell it which direction it's facing. It's the left bumper and whatever the D-pad buttons you want. And so those can just be combined. So then we could still use the D-pad for other things if we wanted. We could have the D-pad assigned to other tasks, and it would only ever do this when it was the and button, when it was the left bumper and the D-pad. The operator has a bunch more bindings, so there's a lot of different climb tasks and stuff, but they're all just all the different buttons they have set up here. The joysticks get bound a little bit different. Those happen in their commands. So we do have them show which ones they are, so like what actually comes out of the joystick. So get drive Y allows us to tell it what the left stick from the joystick is. Get drive X is the same way, so where it's moving, and same with rotation. So if we wanted to drive in a different way, say we didn't want to use the triggers to rotate the robot, maybe we wanted to use the right stick, we could just change this method here, get drive R, and we could send back the right stick X-axis instead, and that would change how the robot drives. Same with the climber, we could move it to a different joystick or have it do it in some other way, and we could change how the robot climbs as well. Anything I didn't cover. That's most of what I want to do. There's a couple things we can see real fast. So the simulator is running, so I'd started it. I can restart it here so we can see what it takes to restart it. So we can just tell it to simulate robot code, and it will compile the code, so it basically goes through and makes sure it's actually able to run, makes it to where it would normally, if it wasn't doing simulation, it would actually send it over to the robot and download it to the robot. Here we're just simulating, so it builds it all, sets it all up, and then we tell it to just run the sim GUI, and it creates this little window here, and we can actually see some of the different methods. So if you have like an Xbox controller, you can plug it in and you can make sure all of the button mappings are doing somewhat of what you expect. Some of the joystick mappings and things, you can actually see some things when it actually works. Let me see how this works. So I think if I go into teleop mode and I tell it, if I like move one of the joystick axis, you can start seeing the motors move. So these are the different these are roughly what is happening to the motors. The issue right now is I don't have the simulation's a little bit messed up with the way the gyro works, and so the steering motors are like freaking out, and so the simulation doesn't work very well with those. But the actual drive motors do work, so if I tell the robot to drive forward or backwards, they'll actually drive roughly where we tell them to, or try to briefly. At some point we had the simulation working, but it's stopped at the moment. If we switch it over to Auton, it'll actually move to like the right starting spot for the 5-ball. It doesn't actually move correctly because the motors are messed up right now. But it at least has some idea of how it works. So at some point we should be able to see the robot actually on the field and have it actually move around a little bit as well. When the simulation's working, we can actually see our dashboard program. So this is called Shuffleboard. And so this is how we can see some of the things going on with the robot. And this is like the communication and like information that the robot sends back to us at the driver station. So there's a lot of diagnostic stuff. Anything we want to see back from the robot, we can get data a lot of the time. So this is also how we can change the autonomous mode. So before a match, depending on whatever autonomous mode we're running, we'll tell it, okay, we're running the double ball auton and we're going to be running it from the left or something like that. So whenever we run 5-ball, it always runs from the right. And so there's different combinations for each autonomous mode that we have. We could probably do this all as a single selector, and we probably should have, but at the beginning we didn't know exactly what the autons were going to be, so we wanted to make sure we could do both the position and the autons separately, and I don't think we've messed it up too many times this year. It also goes through some other things, so it tells us like how far away the limelight thinks it is, if the limelight were connected here, if the compressor's on or off, a lot of the different things about the swerve drive, so each module, which way the wheel's pointed, how fast it's moving, if it is moving, how far the actual robot's moved in the distance, X and Y, some of the control values coming back. So these are like the actual Xbox controller values. So in case something isn't quite working right, we can see if something's being, what the commands are actually giving back and forth or what the driver's actually giving back and forth, we can look. We basically do this for each of the subsystems. We have some features coming back. If we have sensors, we can tell if they're on or off. Anything like that. You can also make a lot of these things go into graphs, so we can graph the velocity, see it like start from 0, see how fast it speeds up. There's a lot of different tweaking and tuning you can do from all of the data that you can get here as well. And this is called Shuffleboard. Yeah, we don't use the gamepad stab. That was an old one. Some of this stuff will be changing for next year. We might still be using it. We're not sure. I know they're updating a decent amount of what kind of like the default stuff for us is. So some of this might change or get improved, but a lot of this will be similar to what we'll have to do next year. All right.